The quiz that I posted last week was difficult. So before I continue, I'm going to show exactly what you'd need to do to solve this. So I had a right-angled cone. Let's say that the height of this object is h, the radius of this is r, and the side length is L. So just like in this picture here. And then I gave the formulas for both the volume and the surface area. So the volume of this region, the volume of this shape is equal to pi divided by 3 times r squared times h. And then I also gave a formula for the area of this. The area is equal to pi times r times the length L plus r. These are the two formulas that we've got. And even further than that, I said, let us only consider cones whose surface area is equal to 1, and then optimize to find which of those cones has the most area. So what dimensions does that cone need to have? Right now, it looks like I've got 3 different variables here. And what I was hoping people would notice is that in a right-angled cone is this right triangle. The legs have length h and r. The hypotenuse has length L. So L is actually the square root of r squared plus h squared. And I can use this information to get rid of at least one of those variables. My goal here is to have a formula that's just a function of a single variable, and then use the derivative to perform my optimization tests. So I will replace that L. That's actually square root of r squared plus h squared, and then plus another r. Okay, well, that looks a little bit better. Next, what I'm going to do is, because this area must be equal to 1, I'm going to start solving for h. Be a little bit easier to isolate that h because there's only one of it. So if this equation is true, I can divide both sides by pi times r. 1 divided by pi times r must be the square root of r squared plus h squared, all plus r. Okay, that looks a little bit better. Let me keep going. I can subtract an r from both sides of this equation. 1 divided by the quantity pi times r, all minus r, is equal to the square root of the quantity r squared plus h squared. Looking good. So if I need to get that h by itself, I will square both sides. So squaring the fraction 1 over pi r minus r is equal to r squared plus h squared. Okay. Then I can subtract an r squared from both sides. So that square that I had before, minus r squared, is equal to h squared. And then finally, one more square root tells me that once I pick my value for R, I don't actually get to pick my H. It is completely determined by this relationship. Let me copy paste that over here. So H is equal to the square root of the quantity, the square of 1 on pi r minus r squared. And what I'm going to do is I'm going to use this formula up top in my volume equation. Now at this point, I'm going to start graphing because I'll have a function of a single variable. I pick my radius, that determines my height, that determines my length, that determines my volume. So I have a function of a single variable. Let me clear all of this, turn my coordinates back on. So my volume function will be equal to pi divided by 3 times r squared. Desmos knows that r is the independent variable, times this square root. Okay. Well, I see a function in there. I'll need to zoom in a bit. So this function is defined, it looks like, between negative 0.4 and positive 0.4. But it only really makes sense to have a positive radius. So I'm only going to be concerned with what's on this half of the drawing. And I can see that there's some maximum here nearby to 0.3. So if you wanted to use a graphing system to help you with this problem, I can just click here. Desmos tells me my R value to find the maximum volume should be about 0.28. I'm going to continue and show exactly what happens when I calculate my derivative and when I perform my optimization. I'm looking for my critical values. Now, I'll have a little bit of an easier time taking the derivative if I rewrite the function slightly. Now, what am I going to do? I'll say that my v function, this is actually equal to pi divided by 3. And r squared is the same thing as the square root of r to the power 4 multiplied by the square root. So I have exactly the same function, just with the formula written slightly differently. And now to take the product of two different square roots, I can just multiply everything underneath those square roots. So v will be equal to pi on 3 times a square root. And what is underneath that square root? I'll have r to the power 4 times 1 on pi times r minus r all squared, minus r to the power 6. And again, I can see that that is the same function, just a slightly different formula. And now let me go ahead and multiply here. Since r to the power 4 is the same as, here we go, r squared, but then squared a second time, I can combine those two different squares and say that this function is pi on 3 times this square root. First, I'll take the square of the quantity r divided by pi minus r cubed. I have to subtract off r to the power 6. And once again, very same formula, very same function, just a little bit of algebraic massage. The reason I have done this is to make calculating the derivative of this function a little bit easier. Now, I know that my derivative, I need to use the chain rule. I have a polynomial inside of a square root. In fact, I know this will be 1/2 times that square root to the -1 power. Or I could say this is 1 over that square root. The chain rule tells me that the stuff inside stays the same, but I must multiply by the derivative of what's inside. Well, the derivative of r to the power 6 is easy enough. That'll be -6. I'll be subtracting 6r to the power 5. And for that squared term, I'm going to use chain rule again. So I'll have 2 times the stuff in parentheses times the derivative of the stuff in parentheses. So here, 1 on pi minus 3r squared. Let me make some more room for that. So here's a formula for the derivative. Now, I can clean this up a bit. I can move this term up into the numerator of the fraction. That's the same formula. And if I'm looking for critical values, I want to find the values of r for which this derivative is either 0 or undefined. So what am I going to do? If I want this derivative to be 0, then I don't actually care about the constants out front. I don't actually care about the denominator. I only care about what makes this polynomial 0. So I can FOIL this out, and what am I going to get? So when I go to FOIL, I'll have 2 times some stuff, and I'll be subtracting 6r squared, or excuse me, 6r to the power 5. Not too bad. My first 2 terms, I've got r over pi squared. My outer 2 terms, I've got negative. Let's see, I've got 3 over pi is my coefficient, and I've got r to the power 3. Okay. My inner 2 terms, I've got negative. 1 over pi is my coefficient, r to the power 3. And then my last 2 terms, I've got plus 3 r to the power 5. Okay, that's looking all right. But then I need to multiply everything by 2. So I'll have all of this stuff, but each of the coefficients will be times 2. So it's actually 2r over pi squared minus 6 pi over r cubed, minus 6 over pi r cubed, minus 2 over pi r cubed, plus 6 r to the power 5, all minus 6 r to the power 5. Well, that seems like an easy cancellation. So those r to the power 5s are gone. So what is this? It's just a cubic. Now, when can this cubic polynomial be equal to 0? I notice that I've really got here, all of my terms are powers of r, and the smallest power of r is r to the first. So I can definitely factor out an r. And while I'm doing it, I'm also going to combine these 2 different r cubed terms. So I'll have r, and let's divide out a pi as well. So I'll have 1 over pi inside my parentheses. And I'll be subtracting off. What have I got? I guess that'd be 2 over r. And then my r squared term, I combined a pi over 6, a 6 over pi, a 2 over pi. So altogether that should be an 8 over pi, like so. That's supposed to be a 2. So r equals 0 is one solution of this, but I'm pretty sure I don't want 0. That looks to be a minimum rather than a maximum. So what's my other option? Well, r would have to be the number that makes this quadratic 0. So r squared, what am I missing here? This should just be a 2, shouldn't it? Sorry. I am looking at the screen instead of looking at my notes. So if I multiply this through, I get this. R over pi times 2. Yes. So pi there, but not there. That looks better. And let me just double check my notes while I am on this over pi. Yep. Okay. So r needs to be the number that makes this equal to 0. What number does r have to be? R will be 1 divided by 2 times the square root of pi. Now, for technical reasons, Desmos thinks this is a different coordinate system. So let's do this as x equals that instead to get my vertical line. And it does, in fact, pass right through that maximum. So for this function, for this volume function, my critical value, well, I could have had positive or negative, but I only care about positive radii anyway. The number that I get is that my radius should be exactly 1 divided by twice the square root of pi. And there is my maximum, just as predicted.